Have you ever stopped to think about what's really happening inside your computer when you click on an app? Well, it all comes down to one thing: memory. Today, we're going to pull back the curtain on this whole system, and trust me, by the end, you'll see exactly why your computer is built the way it is.
So let's just start with the biggest question of all. I mean, if you've ever sat there drumming your fingers on the desk waiting for something to load, you've experienced this problem firsthand. Why can't we just have one single, giant, super fast memory for everything? Well, it all comes down to a classic balancing act: speed versus space versus cost.
So to really get our heads around this, we're going on a little journey. We'll start with the fundamental need for speed, then we'll dive right into the CPU's inner circle, check out the digital workbench, explore the permanent library, and finally, we'll see how this whole puzzle fits together. All right, first up, the need for speed. Because at the absolute heart of all computer memory design, there's this one fundamental trade-off. It's a constant push and pull.
So here's the deal. The faster the memory is, the more expensive it is for every little bit of space, and physically, the less of it you can have. It's a physics and a money problem. So to solve this, computers use a whole team of different memory types. You can think of them like sprinters and marathon runners. The sprinters are incredibly fast, but they're small, and they have to stay right next to the processor. The marathon runners, well, they're slower, but they are absolutely massive and can hold everything you need for the long haul. This is exactly why one size just doesn't fit all.
Okay, part two, the CPU's inner circle. Let's zoom right into the brain of the computer, the processor, to meet the absolute speed demons of the memory world. We're talking about registers and cache. First up, meet register memory. This is the fastest memory that exists, full stop. It's literally built right onto the CPU itself. So if the CPU is a chef, the registers are the single ingredient the chef is holding in their hand, the one they are about to chop right now. It is that immediate.
Now, what's really cool is the next layer out, which is like a high-speed assistant for the CPU: cache memory. Think of it like putting a few sticky notes on your monitor with phone numbers you use all the time. It saves the CPU from having to make a long, slow trip all the way to the main memory for data it just used and knows it's going to need again any second.
But here's the thing. Cache isn't just one big blob of memory. It's actually organized into different levels. You've got level 1, or L1 cache, which is the smallest and fastest, built right into each core of the CPU. Then there's L2, which is a little bigger and just a tiny bit slower. And finally, you have L3 cache, the largest of the bunch, which is shared by all the different cores on the chip. Each level acts as a buffer for the next one, creating this perfect little cascade to keep the CPU constantly fed with information. And to give you a real sense of the mind-blowing speed we're talking about, just look at this number. The L1 cache isn't just a little faster than your computer's main memory. You know, it's RAM. It can be a staggering 100 times faster. To put that in perspective, that's the difference between a task taking 1 second versus a minute and a half. It's a huge deal.
Okay, section 3, the digital workbench. Now, we're going to take one step out from the CPU's inner circle to the memory that you've probably heard of the most: RAM. This is your computer's main workspace.
The single most important thing to get about RAM is that it's volatile. And that workbench analogy is just perfect. While you're working, your workbench is covered in all your projects and tools. But as soon as you turn off the power, poof, the workbench is wiped completely clean. Everything's gone. This is the total opposite of non-volatile memory, like your hard drive, which keeps all your data safe and sound even when the power is off.
So the R in RAM stands for random access, and honestly, this is its superpower. You know, unlike an old cassette tape where you had to fast forward through every song to get to the one you wanted, RAM lets the computer jump directly to any piece of information it needs, instantly. This makes it incredibly good at juggling all the different apps and files you have open right now.
All right, section 4, the permanent library. So if RAM is just the temporary workbench, where does everything go when you click save? Well, that brings us to the computer's permanent library, its secondary storage. This is it. This is your digital filing cabinet, your archive, your library. It's non-volatile, which means all your files, your operating system, all your programs, they're all stored here, safe and sound, even when the computer is totally powered down. It's way slower than RAM, but it's also vastly larger. And this category covers all the stuff we use every single day. We're talking about everything from the spinning platters of a classic hard disk drive, or HDD, to the lightning-fast solid-state drives, or SSDs, that are so common today. Even that little USB drive in your bag and cloud services like Google Drive, they are all forms of permanent secondary storage.
Okay, final section, putting it all together. We've met all the players on the team. Now let's see how they all work together in this incredibly efficient system that engineers call the memory hierarchy.
This chart just lays it all out perfectly. You see, at the very top of the pyramid, you've got registers, the fastest, smallest, and most expensive memory, sitting right inside the CPU. As you move down the list, the memory gets progressively slower, but it also gets a lot bigger and way cheaper, all the way down to your massive secondary storage. The entire system is just brilliantly designed to keep the CPU fed with data from the fastest possible source at any given second. And you know, this quote from our source material really just nails the why behind this whole setup. Every single layer, but especially the cache, exists to be a buffer, a middleman, to make absolutely sure that the super-fast CPU isn't just sitting around twiddling its thumbs, waiting for data from the slower parts of the system. It's all about one thing: performance.
So let's end on a practical thought here. Now that you know how this all works, if your computer feels slow, what's the smartest thing to upgrade? Well, if programs get sluggish when you have a lot of things open at once, you probably need a bigger workbench, more RAM. But if your computer takes forever just to boot up or to load an application in the first place, you need a faster library. That's an upgrade to an SSD. Understanding this hierarchy literally gives you the power to make your own technology faster.